Of Hong Kong's many infrastructure projects of the 80s and 90s, few were as crucial to maintain an efficient transportation network as the Ting Bridge and Approach Viaduct. Its purpose? To connect the rapidly developing Western New Territories with the urban centres of Kowloon, Hong Kong Island and the new airport at Chek Lap Kok. The task was to design and construct approach structures and a cable-stayed bridge spanning the 900-metre wide Rambler Channel between Ting Kau Headland and Ching Yi Island. In August 1994, the design and build contract for the Ting Kau Bridge and Approach Viaduct was awarded by the Highways Department to the international Ting Kau Contractors joint venture. The successful tender was based on a unique design developed by Schleich Bergemann und Partner in Stuttgart, Germany. It features an 1,177-metre long cable-stayed bridge with 2 main and 2 side spans supported by 3 slender, single-legged towers. To withstand the extremely high wind loads encountered during typhoons, cross struts below deck level and transverse cables were introduced to give the towers the required lateral stability. 2 separate decks on each side of the towers contribute to the slender appearance of the bridge, while acting favourably in heavy wind conditions, with design wind speeds of up to 95 metres per second. On site, the contractor established a technical department to carry out the necessary temporary works designs and to determine construction methods and sequences. During the entire construction period, this office provided the link between activities on site and design. Throughout the project, representatives of the Highways Department worked closely with the contractors and designers' site staff to review progress and identify any areas of concern in order to enable a fast-track approach to the construction. Representatives of the joint venture, comprising Cubiertas and Entrecanales of Spain, Zublin of Germany, Downer of New Zealand and Paul Y of Hong Kong, regularly visited the site for progress reviews and meetings with the client. Groundbreaking for the first foundations took place in February 1995. Extensive earth moving in the area of the approach viaduct and ramps was carried out in very difficult terrain, including a nearly vertical rock face adjacent to the busy Tuen Mun Highway, where the slopes had to be cut back to accommodate an additional traffic lane and the 2 approach ramps. Close to roadways, and in areas where slopes of up to 45 degrees were encountered, foundations for the approach piers were excavated as hand-dug caissons. This method used to be common practice in Hong Kong, with husbands and wives working in teams. 115 such caissons, 2.1 metres in diameter and up to 35 metres deep, were excavated. After reaching foundation level, each pile was reinforced and concreted. The extensive earthworks in the immediate vicinity of a major highway called for strict safety measures. Multi-layered wire mesh and netting was installed on the slopes to protect motorists while excavators worked close by. In all, nearly 750,000 cubic metres of material had to be excavated. Traffic disruption was kept to a minimum, but at times everything had to stop. The locations of the three towers each presented different problems, and different solutions were developed for the construction of their foundations. At the Ting headland, site of the northern tower, rock breaking and blasting to a depth of 7 metres below water level was carried out, while an additional area was reclaimed at the shore to provide protection of the foundation against potential ship impact. This reclamation included a jetty for the delivery of all plant, equipment and materials to the works area. After clearing of bedrock to level steps, reinforcement steel was placed for the construction of the 4,000 cubic metre pad foundation. The concrete was ferried in by custom-built barges from the loading facility at Ting Island on the other side of the channel. The barges were designed to carry up to 9 concrete trucks. Dredging was carried out elsewhere under the island, and wick drains were driven into the remaining mud to accelerate consolidation as the reclamation progressed. The island was then formed by placing more than 500,000 cubic metres of rock and sand fill. Its location took advantage of a high point in the underlying rock formation, which reduced the quantity of fill that would otherwise have been required. After completion, the island provided protection against potential ship impact and lateral stability to the tower foundation, while acting as a working area for the piling operation and construction of the pile cap. 52 piles with a diameter of 2.5 metres and an average length of 27 metres were excavated by grabs inside temporary steel casings. Prefabricated reinforcement steel cages were then lowered into position and the piles concreted with tremie pipes to 3 metres below the surface. After completion of the piling operation, Fill material was excavated within a 35 by 40 metre sheet pile enclosure, which marked the outer limits of the pile cap. The pile heads were trimmed using jackhammers and breakers. For the construction of the pile cap, 1,300 tonnes of reinforcement steel were fixed, including 12 layers of bars at the bottom and 9 layers of bars at the top. The weight of these bars required temporary steel frames to be installed as supports. Concreting of the 5,800 cubic metre pile cap was carried out in one single pour. In a 75 hours non-stop marine operation, 4 barges ferried some 820 truckloads of concrete across the channel. The large volume of the pour necessitated the use of chilled concrete and the installation of 700 metres of cooling pipe, through which water was pumped to control the temperature development in the concrete. For 3 days and 2 nights, trucks rolled on and off the island in ponderous succession, accompanied by the endless sound of pumps and vibrators. By dawn of the 3rd day, what was at the time the largest single reinforced concrete pour in the history of Hong Kong was successfully completed. Dredging for the Southern Tower foundation was carried out on the seabed, where the shoreline of Qingyi Island plunges steeply down to the water. Here, a 29-metre diameter semicircular coffer dam was constructed. Temporarily braced by a steel frame, 95 prefabricated H-section concrete units were positioned in a previously blasted trench at depths of up to 22 metres. Alignment and verticality were strictly monitored above water level and by divers working in the trench, notifying any anomalies to their controllers. After the cells of the prefabricated units had been concreted, the toe of the coffer dam was sealed with 3,000 cubic metres of underwater concrete. After dewatering and trimming of bedrock to level steps, a 5,000 cubic metre mass concrete block was cast to raise the top of the foundation above water level. Starter bars for the towers were cast into each of the foundations, and with the bases firmly established, the project was ready to move into the next phase. Given the extremely short project time, a decision was made early on to construct the towers in slip forms. In this method, concrete was poured into steel shutters, which were continuously raised with hydraulic jacks operated from a central control panel. Slip forming with high-strength concrete progressed at a rate of up to 4 meters per day. The towers, rectangular in shape with semicircular sides, were formed in 3 vertical sections of decreasing plan area, separated by transition slabs. At each of these transition slabs, the slip-form assembly was dismantled and replaced by conventional curved shutters. This facilitated the fixing of up to 335 tons of reinforcement steel per transition. The up to 8-meter thick slabs were then cast in the conventional manner. Slip forming for the remaining section of the tower continued by night and day. At the top of the towers, a special slip-form configuration left a space for the later installation of the steel tower heads, which housed the stressed anchors of the deck stays and tower stabilization cables. Two 17-meter diameter circular foundations, each 11 meters high, support the end pier at the Ting headland, which links the approach structures to the cable-stayed bridge. These foundations were concreted in 2.2-meter high, 500 cubic meter lifts. Ring walls containing rock fill on top of the foundations give additional mass. The pier's 2 columns, 60 meters high, together with 2 neighbors of similar height, were constructed in slip form. The remaining 17 piers, with heights between 13 and 50 meters, were constructed in 4-meter lifts using conventional crane-lifted shutters. Over 1.6 kilometers of road decks for approach viaduct and ramps were constructed as hollow pre-stressed concrete box girders, spanning up to 115 meters. Where the decks are high above ground, they were constructed as balanced cantilevers, rigidly connected to the supporting piers through pier heads. Up to 10 formwork travellers were used, moving outwards from each side of the piers in 4 to 5 meter increments. These slender structures express strength and elegance in equal measure. Across the end pier spans a 64-meter crosshead, which houses the rocker bearings of the cable-stayed bridge and the bearings of the approach decks. In the centre section of the viaduct, where road decks are closer to the ground, construction was carried out on false work. Spans were concreted in 4 up to 22 meters long segments. After completion of a span, reaching about a quarter into the adjacent span, the box girder was pre-stressed and formwork and false work were moved to the next span location. Abutments, heavily ballasted with fill material to prevent overturning, acted as counterbalances for the single-deck cantilevers where construction was carried out over the Tuen Mun Highway. The fabrication of the 6 tower heads, which house the stressing anchors of the bridge's stay cables, was carried out in nearby Shekau. The bearing blocks for the anchors were welded to the tower walls before the tower heads were assembled. These enormous steel boxes each weigh up to 190 tons and are up to 31 metres tall. The form tubes for up to 88 stay cables per structure had to be fitted with an accuracy of ½ a degree. At the same time, welding of the airtight cross-strut boxes was carried out. Works in the same yard also included fabrication of the 360 main and 530 cross girders for the composite road bits of the cable-stayed bridge. After fabrication and painting, individual girders were transported to 3 pre- and trial assembly areas. There, 2 main and 3 cross girders at a time were welded into 13.5 metres long grid units. The entire bridge was then trial assembled, 5 grids at a time, and specified bolt holes for the main girder connections block drilled to ensure correct alignment and fit of the splice plates during the deck erection on site. At the base of each tower, preparations were made to install the heavy lifting system to be used for raising the steel tower heads and starter panels for each of the decks. 2 200-ton strand jacks were mounted on each side of the lifting beams, which had been stressed to the tower concrete. With the heavy lifting gear in place, the site was ready for the delivery of the steel components. In March 1997, the tower heads for the Ting Tower arrived by barge from Shekau. With the heads safely offloaded, it was time to ask the gods for their blessing upon the next formidable stage of the project. Aye. Then it was back to work. A pathway was marked out for the multi-wheeled flatbed hydraulic trailer to carry the tower head to the exact position at the base of the tower where the lifting gear would be attached. On the Ting side, the tight space between the tower and an adjacent rock face required additional movements before lifting could commence. Using the rear section of the trailer and the heavy lifting gear, the tower head was inched to the vertical, ready for its stately ascent to the top of the tower. Once the tower heads had reached their final height, they were slid inward into spaces left open for them. There, all elements of load transfer were installed, and the remaining tower section was concreted directly against the tower heads. May 1997 marked another record achievement for the project. The unprecedented 200-ton heavy lift of the two 9-story tall tower heads for the central tower to a height of 200 meters. The first deck segments to arrive on site were the two starter panels for the Ting Tower. These vast assemblies, measuring 23 by 16 meters, were offloaded from the barge by night when sea conditions were calm. Even then, extreme care was necessary. The limited space at the base of the tower required that the grid be transported in the vertical position. Dubbed the rocket launcher, a 20-metre steel frame mounted on a pair of hydraulic trailers held the grid as the assembly made its snail's pace approach to the lifting position. By dawn the next day, the heavy lifting system on top of the tower had lifted the 60-ton panel into position some 70 metres above the ground. The panel was then pulled inwards to engage hinges temporarily attached to the tower. Over a period of 3 hours, the panel was lowered into its final position, joining its previously installed twin on the other side of the tower. In the following months, starter grids were installed at the Central and Ting towers in the by now familiar fashion. Following the erection of the starter panels and the lifting of the steel cross struts, transverse tower stabilisation cables were installed between the lower transition slabs and the cross struts, and from there to the tower heads. Like the mast of a sailboat, the slender tower now has the required stability to cope with high wind loads. Precast concrete deck panels, 4.5 metres square, were placed onto the steel grid of the starter panel to complete the first segment of the composite deck. In a typical grid, 12 such precast panels were placed and the joints concreted to give the segment its composite characteristics. Many hands make light work. Well, sometimes. Manhandling the high-density polyethylene sheath for the stay cables was certainly labour-intensive, but it was also an excellent boost for the team spirit. The deck stay cables consist of up to 58 strands of 7 galvanized wires. Each of the strands was individually installed between the dead anchors at deck level and the stressing anchors in the tower heads. Using a wheeled detachable trolley which prevented chafing, each of the strands was pulled up inside the sheath. The sheaths have an external helical protrusion which reduces rain-wind-induced vibrations of the cable. Within the tower heads, each of the strands was stressed by isotensioning. On each of the 4 deck cantilevers originating from a tower, a stiff-legged derrick crane was assembled to lift steel grids and concrete panels for the growing bridge decks. The grids were typically 18.8 metres wide and 13.5 metres long between cable anchorages. Alternating on each side of the tower, new grid pairs were connected to the already completed deck cantilever with splice plates and high-strength friction grip bolts. At the cable anchorages, the new grid pair was joined by connecting cross girders. The erection of the first grids adjacent to the towers provided valuable experience and allowed a reduction of the deck erection cycles to as little as 4 days. In an erection cycle, a new grid pair was lifted and connected, 2 pairs of stay cables were installed, 24 precast panels were placed and concreted, and the derrick cranes were moved forward, ready for lifting of the next grid. Over a 4-month period, 75 grid pairs were erected from all 3 towers simultaneously, adding over 1,000 metres to the bridge deck. December 1997 marked the all-time high in the history of the project, when 2,680 tonnes of steel, 1,200 tonnes of stay cables, and 11,200 square metres of deck were erected in a single month. As the deck cantilevers grew in length, temporary cables had to be anchored into the tower foundations to prevent excessive movement of the decks and deflections of the tower tops in high wind conditions. Just prior to being connected to the adjacent decks, the balanced cantilever of the central deck reached the unprecedented length of 556 metres, making it the longest free cantilever deck ever erected. To give the central tower the necessary stability, both during the construction phase and under permanent loading conditions, longitudinal stabilisation cables were installed. From the top of the central tower, these cables run to deck level, where they are anchored adjacent to the two side towers. At a length of 465 metres, they are the longest stay cables ever installed on a bridge. At the two shorter side spans, rocker bearings were installed to give vertical support to the bridge decks while allowing thermal expansion and contraction. "36 months after groundbreaking, the last gap between the central and Ting deck cantilevers was closed with a special closure segment. As the last stay cable adjustments were made, the project teams of contractor and client witnessed the culmination of 3 years of intense effort. The realization of an inspired design and the completion of an engineering masterpiece. On May the 5th, 1998, the Secretary for Transport, assisted by representatives of the joint venture and the client, officially opened the bridge to the public, giving Hong Kong a new landmark which will lead the way into the new millennium.